the film. The thickness of about 10 nanometer was the minimum thickness attainable for this system, and further compression did not squeeze PVD molecules, but result in the increase in the applied load. Then, triangular voltage signal was applied to the lower surface, and friction force for the upper surface was measured. SFA friction measurement has a unique benefit that cannot be obtained by other friction measuring techniques. As I already told you, SFA not only measure friction force, but also thickness D and area A by the observation of filter fringes. Then, uh, as you can see, the contact geometry, sliding geometry, is exactly the same as the famous quick flow geometry. So we can use this equation and calculate the effective viscosity of molecularly thin film directly used by the friction experiments. So frictional result is quantitatively described by the dimension of viscosity. Please note that this viscosity is completely different from bulk viscosity because of the confinement effect. By using effective viscosity as the quantitative parameter, we can directly compare the results of the friction measurements with nano-rheology measurements. This is a big advantage of using SFA for thin film shear experiments. The results of the nano-rheology and tribology are plotted together as the relationship between viscosity and shear rate. Result of the nano-rheology is described here. And as you can see, for the thick film, thickness of about 200 nanometer, almost constant viscosity was observed like a Newtonian liquid, and the viscosity is equal to the bulk value. Decreasing thickness gradually shifts the experimental shear rate range into higher direction, and we see shear thinning behavior here. Thickness of 10 nanometer was the minimum thickness attainable for this measurement. The nano-rheology curve apparently shows shear thinning. Shear thinning is the viscosity decrease with the increase in the shear rate. This shear thinning behavior here. These are the results of the tribological measurements. Thickness was about 10 nanometer for all the plots, and the effective viscosity calculated from the friction force and thickness exhibited shear thinning behavior. Please note that the extrapolation of these shear thinning plots of the tribological results nearly overlap with the shear thinning of the nano-rheology curve for the 10 nanometer film. Now, let me explain how to understand the observed behavior. Let's consider the relationship between force and velocity. For simple Newtonian liquid, force is proportional to velocity. On the other hand, for solid-like friction system, friction force is not dependent on the velocity. Now, we convert this relationship into viscosity versus shear rate using this equation. For Newtonian liquid, viscosity is constant. On the other hand, for solid-like friction system, force or stress is constant. So viscosity should be inversely proportional to the shear rate. So if we plot on the log-log scale, effective viscosity for solid-like friction system should follow on a straight line with a slope of -1. We come back to the experimental data, then we clearly see the shear thinning, shear property transition from Newtonian-like constant viscosity to solid-like friction slipping behavior, shear thinning with the slope of almost -1, along with the thickness decrease. These tribological results can be, of course, directly compared with bulk rheological measurements. These are our results. We measured the friction properties of linear polyisoprene having two different molecular weight. This low molecular weight sample exhibited no chain entanglement effect, and 48,000 extensive entanglement. Then these two materials shows very different sliding behavior in confinement. As you can see, the low molecular weight sample apparent shows a shear thinning with the slope of almost -1. And for the 48,000 film, almost constant viscosity like Newtonian liquid is observed. When we contrast these results with the bulk rheology measurements, we can see that liquid-like to solid-like transition for the low molecular weight sample, constant viscosity to the shear thinning with the slope of -1, typical solid-like shift of the behavior. And for 48,000, we do not see the transition, and liquid-like properties also observed for the confined films. Linear 48,000 sample has extensive chain entanglement effect, and when we compress the two surfaces, these molecules produce large non-equilibrium repulsion. So molecules are difficult to be squeezed out from the contact interface and still be in the gap, as is random coil conformation, which is not very different from that in the bulk states. This should be the reason that linear 48,000 exhibited liquid-like flow even in molecular scale confinement. Our PIP results implies that the transition from liquid in the bulk to solid-like state in confinement could occur when the confined film reaches its hard wall state, namely minimum thickness attainable for the system. I measured the effective viscosity behavior for many different commercial lubricants, from simple liquids to polymer melts, using the surface forces apparatus, and also made a comparison with published results. Surprisingly, the effective viscosity for many different liquid lubricants in their hard wall states seem to follow on the universal shear thinning equation. As I already described, geometrical confinement has an effect to rearrange molecule into dense packed structure. This diagram schematically shows the typical explanation of bulk glass transition of liquids at low temperature. We can consider that effect of decreasing thickness on molecular volume should be basically equivalent to that of decreasing temperature for bulk glass forming liquids. Then solid-like shift of liquids in confined geometry could be the similar physical origin of the bulk glass transition near TG. We assume that the local patting structure of liquid molecules in the hard wall film could roughly correspond to that in the bulk liquids at or near TG. Then, this existence of the universal shear thinning equation for confined hard wall film is basically the same observation of the universal viscosity curve of bulk glass forming liquids at or near TG, which is well-known fact included in the famous WLF series of polymer rheology. Actually, this universal equation is verified by computer simulations in 2012. Paulson et al. Carried out the friction calculation of confined hydrocarbons and obtained the shear thinning behavior, which is basically the same as our experimental results. The calculated shear thinning equation, quantitative parameters at room temperature, was very close to the universal equation based on our SFA experiments. Now, let me come back to the topic of updating Stevens curve for smooth surfaces. As I already described, the horizontal axis of the conventional Stevens curve is not appropriate, so we measure as a function of sliding velocity. Based on the SFA experiments, Jacob Vislarchibili proposed new viscosity map and friction map for smooth surfaces which quantitatively bridge rheology and tribology. I added some improvements, existence of the universal equations for the effective viscosity in the hard wall state. Also, I did some experimental verification of their viscosity and friction map by studying the shear behavior of industrial lubricants. These representations should be more quantitative and possibly more accurate than conventional Seebeck curve, but difficult to draw experimentally without SFA. Therefore, I will show you more instinctive modification of the conventional Seebeck curve. These slides show the conventional Seebeck curve again, but please note that the horizontal axis is not the Hersey number, but velocity. In the conventional Seebeck curve, friction at boundary regime is very large because of the collision between surface asperities. For updated Seebeck curve for smooth surfaces, no change should be made in the EHL regime. But this Newtonian like force velocity dependence is not valid at a low velocity range. Friction should be extensively high in this regime. The whole curve shape is rather similar to the conventional Seebeck curve. However, the physical origin of the large friction is totally different, and this large friction comes from the confinement-induced viscosity increase and solidification of liquid lubricant. Now, finally, I will briefly talk about the very different behavior of water-based lubrication. Water-based lubrication received considerable attention for these decades because of its environmentally friendly and sustainable benefit. In addition, water-based lubrication is a fundamental mechanism of biological friction interface. This very low friction is based on the water-based lubrication. As lubricant liquid, oil and water are totally different between each other. As I already described, as regards oil, decreasing temperature or geometrical confinement increase the density of the fluid, which result in the viscosity increase, and sometimes solidification of the system occurs for oil lubrication. However, very different mechanisms are in water. Geometric confinement could increase the molecular density of water molecules, but this does not induce solidification. Major interaction between water molecules is hydrogen bond, which is strongly orientation dependent. Solid ice is less dense than liquid water. Because of this, water molecule retain its high fluidity even in nanoscale confinement. This is the principal mechanism.
Another actually another 3 more minutes.
3 minutes, okay. This is the principal mechanism of the extremely low friction of water-based lubrication. Let's consider the Seebeck curve for smooth surfaces separated by water-based lubricants. As I already described, Seebeck curve for smooth surfaces lubricate oil exhibit large friction in the boundary regime due to the increase in the effective viscosity of liquids, oil. On the other hand, effective viscosity is still very low for confined water in boundary lubrication. So, Seebeck curve for water lubricated system should be low over the entire velocity range. However, this extremely low friction does not always appear. Careful surface design should be required for the low friction. High fluidity of water, even in molecular scale confinement, means that water molecules are easily squeezed out from the contact interface by applied load. So sliding surfaces should have structures such as ions, charged or polar groups that form large hydration shells that generate steric repulsion in short-range interaction. Then the hydration layer at the contact interface act as very slippery intervening films. These slides show the boundary friction of oil-based and water-based lubrication measured in my group. This molecule, a BIPA, actually used in cosmetic fields, is water-soluble amphiphilic polymer, which forms a large hydration layer at the sliding interface and exhibit extremely low friction. The friction coefficient is of the order of 10 to the power of -5. Now, today, I described the updated the Strebeck curve concept to bridge the gap between biology and tribology, and describe how different behavior is observed for oil-based and water-based lubrication systems. I'd like to thank these people, particularly these two best respected professors, Jacob Srachili and Mark Robbins, who untimely passed away in the last few years. Thank you for your attention.
Okay, thank you very much, Professor Yamada. Now the paper is open. Are there any questions and comments?
Participants, so actually if you have any queries, you can raise your hand, or you can even chat, you can put it in chat box.
Okay, Professor Yamada, actually it's a very nice, very interesting result. And actually I'm kind of stranger in this field, but do you have any idea to apply your result to your product, like your cosmetic or something?
Well, actually, I performed experiments many for industrial, particular cosmetic lubricants, and actually, the cosmetic lubricants are used in the condition not very severe as machinery conditions. So
I see.
the very different sliding behaviors observed on skin surfaces or hair surfaces, or sometimes sometimes floor surface, dish surface. They are used in commonly in detergent. So in order to control the desirable friction properties, it is very important to understand the thin film neurological and tribological properties. So and it is difficult to show you the direct application research here, but many research is applied to design desirable surface sliding properties of our products.
Okay. Thank you very much. I think maybe we're going to move to next paper.
Okay, thank you very much.
Okay, thank you very much. Oh, actually one.
No, Sensei, it is announcement. Okay, so.
Oh, yeah, okay. Yeah, thank you. So maybe we're going to next paper. The next paper is, again, the invited lecture 2, resistive switching, photoabsorption, and DNA biocapability for ion irradiated titanium oxide 110 by Professor Shikha Barma, Institute of Physics, Bhubaneswar. So, Professor Barma, can you start?
Yeah, can I share my screen? Yeah.
Yes, yes, please.
Yes,
So are the slides visible?
yes, ma'am.
Okay, so can I start?
Yes, please.
Okay. So thank you, Professor Kimura, and I would like to also give thanks to the organizers for giving me this opportunity, especially to Dr. Karthien and also Dr. Shivalingam for giving me this opportunity to give talk in ICONN 2021. I am from Institute of Physics, Bhubaneswar. It is in state Odisha, and we are a department of atomic energy. let me just switch on this. So we are at Department of Atomic Energy, and I'm from Institute of Physics. And what I'll be talking about is some phase transition in TiO2, and then also, of course, the resistive switching behavior and the DNA compatibility in these ion irradiated materials. So TiO2, for this audience, it is not a new material. It is important in photocatalysis and photochemical applications. And these TiO2 surface states have been shown to play important role in the photoelectrolysis of water. And this is a non-toxic material with many interesting optoelectronic properties. And it is used in solar cell, chemical sensor, photochemical cells, etc. And they show interesting switching behavior. And it is highly biocompatible, as our previous speaker, Professor Yamada, showed us that it's it has a biocompatible nature, which is very useful in many implants, where of course these kind of wetting behavior makes a lot of interesting usage. So I'll talk a little bit about the interaction of TiO2 with the DNA, biological material. So regarding this photoabsorption and photocatalysis, TiO2 has a wide band gap. And due to the wide band gap, it's only the UV light which is able to promote an electron from the valence band to the conduction band. But once this exciton is generated, electron and hole can be separately used for reduction and oxidation process. However, they recombine very quickly in less than 30 picosecond, and hence the efficiency of photocatalytic behavior is low. And the efficiency of photocatalysis depends on how well one can prevent this charge recombination. So what we would like to do, or what the device people would like to do, is keep these electron hole as far separated from each other as possible. So the high intrinsic band gap of TiO2, which is 3.2 eV in the case of anatase, and this I will show the anatase and rutile structures, crystalline structures. I'll show you in next slide. It is band gap is 3.2 eV for anatase structure and 3 eV for rutile structure. And because of these high band gaps, absorption is only possible in UV part of the solar radiation, which gives only 4% efficiency. So the efficiency is very low for this material if we work only in the UV regime. So all photon-driven applications of TiO2 require UV light for excitation. It is therefore critical to make TiO2 absorb light in visible range in order to facilitate its applications into the field, such as photovoltaics and visible light photocatalysis. So these are the crystalline structures of rutile and anatase, and the band gaps are slightly different. And studies have shown that by simple annealing, one can transform from anatase to rutile at about 800 degrees C. And this is also shown in the coming slide. So, but first let me just give a brief outline of what this talk is about. So in the first section, we'll talk about the phase transition and resistive switching properties and the photoabsorption properties of these materials once they are irradiated. And then we'll put DNA, one biological material, on these TiO2 surfaces and see the interaction. So this is how the phase transformation from anatase to rutile occurs. If you see, this is a rutile seed and all this is anatase, and as one increases the temperature, whole anatase phase transforms into rutile. So it is the big rutile crystal that forms. And this continues further as the 800 degree, at 800 degrees C, the time increases. So these are the TEM images. So absorption of anatase particle into rutile is seen after heating. And this also, the development of anatase into rutile can happen at the interface, it can happen from the surface, or it can happen in the bulk. So this is basically a time and temperature curve for the three dominant regions, how the phase transformation occurs. So what we have done is we have seen these phase transformation in absence of any annealing, but through the ion implantation. So this is a TiO2 film, which is sitting on a gold layer. This is very thin film. It is only 80 nanometer thick. And when these ions go inside, they are going up to the range of 32 nanometer. So the ions go and sit somewhere here. But the more important, when these ions go in, they create lots of changes in the film. For example, they can create oxygen vacancies. This oxygen may go out of the surface a little bit. So it will become little deficient in oxygen on the top. And it may, on the other hand, create titanium-rich centers. Okay, that those produces nanoparticles, nanostructures on the surface. And what we have studied the phase transition in this film, and also the resistive switching of these properties as we go along. So this is the XRD image. This is for the clean sample, and this is as we increase the dose of titanium during implantation in the system. So this is the anatase feature, and this is the rutile feature, which is coming from the XRD. And as one notices in the beginning, although A and R are roughly equidistributed, but at very high fluence, it is mostly R is much higher than anatase. So at this stage, somewhere around 1 to 13, if you see, some kind of phase transition has started happening. Now, if you see here also, initially, if you see, the anatase increases slightly but goes down, but rutile really takes over. It is really going high. Same thing is for this AR by AA ratio also, that if you see, the rutile has taken over. This is the area of rutile to anatase, and this is the weight fraction of rutile. Interesting thing is, if you look at this region of anatase, one can get the crystalline size of the anatase particle. And what one sees is that although in the beginning anatase is larger in size, with fluence, the size has decreased. And the reason, as we will see when we go further, that this big anatase particles have got absorbed into rutile to form the big rutile seed, whereas these particles only remain once the phase transition has taken place. And the reason that anatase small particles remain is because of their surface energy. Okay, this we will see as we go along. So this is the Raman experiments. This also shows the similar thing, that although there are all anatase and rutile at various fluences, but if we blow up this small region and see, this is the rutile feature, this is the anatase, and this is one feature which is coming due to the nano anatase or from oxygen vacancies. As I told you, oxygen has gone out, so some vacancies have stayed back. This is the anatase portion coming from the oxygen vacancies. And again, when we plot AR, the rutile area divided by the anatase area, what we see that overall it increases at beyond certain point, around 13, and we are seeing the phase transition. So anatase gets converted into rutile. So this is the sort of brief summary of what happens. This anatase particles, they join together and they become part of this rutile. Orange is the rutile, so they get absorbed into rutile. But some few anatase small particles may remain. And the reason is that the free energy of rutile is actually lower at ambient pressure and temperature. So it is more thermodynamically stable. So at long time and high temperature, it will be all rutile. But surface energy of anatase is lower. That is in nano form, that is when small anatase is there, it is kinetically more stable. So in the end, even at high temperature, for example, in this stage, you will see some few small anatase will be there, but otherwise mostly will be rutile. And we have some stage like this, we have a small anatase. So it is basically a competition between growth and transformation of anatase, and oxygen vacancies also play a role. How do we know about oxygen vacancies? Is we do X-ray photoelectron spectroscopy. This is X-ray photoelectron spectroscopy, and this is the Ti2p region using XPS. So this is the Ti4 plus state. One can understand oxidation states using the XPS. And this, if you see the little one which grows with fluence, is the oxygen vacancies. So oxygen vacancy will appear something like this, that one of the oxygen is missing. And this causes the decrease in structural rigidity also. So presence of oxygen vacancies make morphological changes as well as it makes chemical changes, and it decreases the structural rigidity. So these are some TEM images. This is for the pristine sample. If you see, there is TiO2 sitting on gold, nickel, and silicon. And this is the high resolution TEM that we see anatase. This white contour is anatase, and the black contours are the rutile portion. These are the FFT images. And if we irradiate this pristine sample at 1:14, what we see, the anatase nanostructures have decreased in size, whereas rutile increases. And at 1:15, it's mostly rutile in the film. So that's how we know that the phase transition has occurred in the system. Now, once we go to the resistive switching of these same films, so the surface of these films have nanostructures on the top. And this is atomic force microscopy. So we are measuring the forces between the tip and the surface. And this is the same image, but here we are looking at the conducting properties, IV properties of the surface. And these regions, they are showing, the lighter regions are showing that the current is showing. It's current from somewhere here, it is showing. And if we show the profile, then height is blue in color and current is red in color. So there are places where the current becomes very high. And if we do the IV characteristics, this is done at same voltage. If we do the IV characteristics, it looks like this. So initially the current is low, and this is called the high resistance state. But at some point, this resistance becomes lower, okay, and the current becomes higher. This is called the V set point. The current goes up, then it increases, and beyond certain voltage, the current starts to decrease, and this is called the V reset. So we have this is called the resistive switching. We are able to switch it from the high resistance state to a low resistance state. And for this case, we are able to use an AFM tip, which has been used as a conducting tip to measure the current between the gold and the tip. And the reason is something like this, that if we have a negative on the top and positive for this gold, this oxygen vacancies are positively charged and oxygen ions are negatively charged. So these oxygen vacancies make conducting path from the top to the bottom, and this leads to the passage of current between gold and the tip. And the reverse happens when it is positive charge. So the switching breaks. In this case, there is a conducting path, and in this case, there is no conducting path. So there is, due to the presence of conducting filament in TiO2, and this is, for all this, oxygen vacancies are important. So this is the photo absorption and band gap tailoring, and this also shows that these are the UV vis curves taken in the photo spectrometer. And here also, if you see that initially the band gap is large and then it decreases. And this is because it is going from anatase to rutile. Here also we see that the phase transformation has taken place. And so the phase transformation has taken place and the resistive switching properties are seen. Next, we go to the DNA, biological material on these nanostructured surfaces. So TiO2 is used in bioimplants, as I said, because of the, it has a very nice properties. It's a bioimplant material. And this is a bone cell anchoring itself on the TiO2 surface. And DNA is a functional material. In designing, it can be used in designing functional nanomaterial. It's used as a programmable scaffold. It is, of course, biocompatible, environmentally friendly, and it has a potential for biosensing. So just a little bit of introduction on DNA. DNA is basically this double helical structure. The backbone is negatively charged, and in between are bases. And these are called the nitrogen bases. And there are 4 kinds of bases, as you may know, AT and GC. Between GC, there will be 3 bonds, and between AT, there will be double bond. About this much is enough for the introduction for DNA. Its radius is about 1 nanometer, and the separation between each base pair is about 0.34 nanometer. So this is some number which you may like to remember. More importantly, that 10 bases are about 3.4 nanometer. So this is like a conjugation between A and T, between nitrogen bases, and this is the phosphate backbone. And as you see, it is a nanomaterial. So we are also working with a DNA, which is also a nanomaterial. And these are some process which can have double helix is combined, but one can break these bonds and make it single strand DNA, and this is again joined back. So this kind of local melting we have seen, as we'll go ahead and see. So functioning of biosensor depends on surface properties, homogeneity, topography, toxicity, adsorption, and of course the wetting properties. So this is a kind of a circular DNA what we have used, and this has a 3000 base pair. It is coming from it is also called plasmid. Okay, this is the kind of DNA we have used. And what we do, if you see in atomic force microscopy, this DNA looks a circular DNA. But once we interact it with mercury salt, it becomes linear. So this is the interesting part, that the circular DNA becomes linear chain-like particle after interaction with mercury. So the mercury, if you see the DNA high resolution AFM, here you will see base pairs which are separated by 3.4 nanometer. They have not been disturbed. And here the mercury is sitting. These are the mercury nanoparticles have been generated within the DNA. This is the IV curve. Alone DNA, if you see it, the IV characteristic looks like something like this, semi-metallic. But once it has interacted with the mercury, the DNA IV characteristics have changed. Okay, and they are all sitting on mica, but this DNA interacted with mercury. Okay, so DNA can be called as a chemical sensor of mercury. It's able to sense the mercury through this IV characteristics. This is again the X-ray photoelectron spectroscopy. This is also something gives very useful information. So this is coming from clean DNA. If you see, it has 3 features, but the moment you interact it with mercury, you will see lots of features. And as it turns out, this first one is due to the unpairing of the DNA. And this is due to the interaction of mercury with the DNA. So for example, in the case of the DNA figure that I showed you, these bonds in between are breaking and mercury is getting engulfed into the DNA bases. So it's something like this, that these are the mercury nanoparticles and these are the base pair, DNA base pairs which we are able to see. This is some quantum chemical calculations also. We show what we are saying about the XPS parts. And so now we have put DNA on the TiO2, like the first studies I showed you on TiO2 surfaces. We took this DNA and put on TiO2 surfaces. These TiO2 surfaces are modified to enhance biocompatibility and better wetting because they have vacancies on the top. And we have studied the morphological parameter of DNA, the size of DNA, as well as some charge transfer. So again, the nanopatterning has again been done using ion radiation. And these are the surfaces, what look like. So they have nanostructures, and the size of nanostructures are of the order of 50 nanometer. TiO2, these are crystalline dots, and they also have oxygen vacancies. And they also show higher photoabsorption and PL behavior. So these are the surfaces which, this is the clean TiO2 surfaces. This is after it has been irradiated at this fluence, 6 into 15, 10 to the power 15, and this is 18 into 10 to the power 50. So this is without DNA. And now once we put DNA, what it looks like is this. And it turns out in all these cases about one monolayer of DNA is sitting on these surfaces, these respective surfaces. Okay. And now you may ask why it doesn't look like cord DNA. So DNA can look in various forms. DNA can look like this, and this is a film of DNA. So this is what we are seeing, kind of a one monolayer film on the surfaces. And whether we'll see this or this or this will depend on the DNA concentration and the concentration of the buffer solution, which is also used. All these are on the mica surface. All 3 are on mica surface. And then if you notice, this is without irradiation, this is after irradiation. And the area, the circle of the DNA, the diameter of the DNA is increasing. And this we are seeing also from here. We can plot the DNA. So DNA diameter is increasing with time. with irradiation. And these are the XPS. This is the XPS from the TI surface without putting DNA. But after irradiation, we are seeing these oxygen deficient peaks, oxygen vacancies. And once we put DNA on them, it looks like this. So the DNA peak is shifted, which shows that there is a charge transfer, negative charge transfer from DNA backbone to the TiO2 surface. So that way XPS is a very powerful technique. And this is some molecular dynamic studies also for one of the bases on the TiO2, which also shows that there is a charge transfer happening upon the DNA conjugation. This is the charge going from the DNA base to the TiO2 surface. And here what we are showing is that for the unirradiated TiO2, this is the oxygen part. So it is not showing, this is the oxygen vacancy was very little. But as you put more and more ion dose into the system, this ion irradiation produces this oxygen vacancy. And this is causing the better wetting of the surface. Wetting improves, and this is the, and because the wetting properties are included, and so the biocompatibility is also increases. So this is what is the cause of this better compatibility, that the DNA circle diameter is increasing because we have a circular DNA. So this is compacted DNA, and this is the spread out DNA because of the better biocompatibility of the systems. So in summary, first we saw the phase transformation in TiO2, and the anatase transforms to rutile at a critical fluence. And the critical fluence was seen from Raman and XRD. And this shows the resistive switching and photoabsorption properties. But with interaction with DNA shows us that the wetting of this surface has also increased. And the reasons are two. One is the formation of nanostructures on the surface that the wetting improves. And secondly is because the vacancies have been created on the surface. And this leads to enhanced biocompatibility. I have not shown persistent length, but the diameter of the DNA changes. And what we have also shown that the persistent length of the DNA also changes. And there is a charge conjugation, that there is a transfer of charge from the DNA to the surface. I like to acknowledge these are my students who have worked in this area. And Dr. Kanjilal, Alok Kanjilal, Shivnadar University. This is our biotechnology collaborator, and also Indian Physics Association. I'd like to say thanks. So thank you.
Thank you very much, Professor Bama. Now the paper is open. Are there any questions and comments?
So participants, if there is any question, so kindly raise your hand, so we will allow you to interact with the speaker, or even you can chat in chat box. Okay, we will read it for you. Participants, don't hesitate. Okay. Yeah. So one question from chat box. Apart from TiO2, what are the other options?
Well, people are also working on zinc oxide, but zinc oxide is not as biocompatible material as TiO2. That has been seen. And also silicon itself, silicon oxide itself, if you look at silicon oxide material, I'm talking in terms of biocompatibility. Silicon itself is actually the reverse of biocompatible. It becomes hydrophobic. TiO2 is hydrophilic, whereas silicon oxide becomes hydrophobic. So that makes the life difficult. But if you want to think about the resistive switching properties are also seen in zinc oxide, but not as good as TiO2. And so, but TiO2 has the advantage that it's showing a good resistive property as well as a good biocompatibility. So in principle, one can go and, so we have studied it for a chemical sensor. One can also see for as a sensor for these biofilms or wetting properties. Also one can.
Ma'am,
See.
actually, in the in pure TiO2 is biocompatible, but if you plant iron, so whether it is okay, still okay,
It is becoming better actually. That's what we are seeing. If you
actually biocompatibility is
if this
more.
is this is the this is done on the clean sample, clean TiO2 sample. This is after irradiation for 10 minutes, and this is after irradiation for 30 minutes. And if you see, wetting is improving, right? This contact angle is decreasing, so the wetting properties are becoming better. And because wetting properties are becoming better, that is why the DNA diameter is also increasing. So that the two things are related. So we are saying that DNA is becoming more biocompatible on ion irradiated surfaces.
So by doing biocompatible, actually contact angle measurement itself, we can tell, ma'am, whether it is biocompatible or not.
Yes, yes. The decrease in this angle will tell you. So because it's becoming more hydrophilic, its wetting properties increasing, and when the wetting properties increasing is synonym to saying that it's becoming more biocompatible.
Okay.
Because when they are putting this TiO2 implants in the body, what they would like to have this less friction and more interaction with the bone cell, right? So for that purpose.
Hi. Am I audible? I have a question.
Yes.
Okay.
Yeah, hi, ma'am.
Hello.
Good afternoon, ma'am.
Good afternoon.
So I missed. I just joined late due to some reason. What was the energy of iron you have used, ma'am?
I think it is 50 kV.
Okay, it's KeV. Okay, so you're basically implanting the irons.
Yes, but the thing is, yeah. Let me see if I can go back to the that slide. It is I'm implanting, and the range is within the film.
Yes, ma'am. It's low energy.
Yeah,
So
it's 50 kV, and the range is 32 nanometer, and our film thickness is 80 nanometer. So these TI, but it is self-ion if you see, right?
yes, ma'am.
We have chosen it so that chemical poisoning is not there at least. So these eyes go and see.
One another point I want to ask that it has been observed in ion irradiation that at sometimes when you keep on increasing the fluence, instead of formation of nanostructure, it results in a smoothing of surface. Have you observed any of such things in your case?
No, we have not. Okay, you mean the roughness, right? Decrease in
Yes.
roughness.
Yes.
In these materials we have not seen, but we have seen that kind of a behavior in indium phosphide. Okay.
Okay.
So you are talking about maybe scaling exponents or something. Yeah, the roughness goes up and then decreases, right?
Yes.
So beta it becomes negative.
Yeah. Oh, okay. Thank you. Thank you.
Yeah. What is your name?
Ma'am, Harsh.
Okay. Good.
Thank you.
Kimura Sensei, I think we can complete. It's time for contribute.
Okay.
Okay.
So
So I
thank you
will
very
stop
much.
sharing. Okay.
Okay. Thank you very much, Professor Pam.
Yeah. Thank you very much for giving that.
Thank you.
Yes.
So we're going to move to next presentation. Next is contributory lectures. First, the CL1, exciton mode transition in an asymmetric double quantum well, Thomas Helmy electric screening, G. Binish, Department of Physics, St. Joseph College, Bangalore, Karnataka, India, and P. Nityananthi, Nanostructure Lab, Department of Physics, the Ganjigram Rural Institute. So the presentation will be by G. Vinish.
Vignesh, are you available? Vignesh? G. Vignesh? I think he's not available.
He's not available now. Maybe he's not here.
Yeah, he's not here, but actually second contributory lecture, so the person is there. The first one he didn't join yet.
Oh,
I'm checking past 10 minutes, so he didn't join.
okay. So
In that case, can we move to
we
second
wait
one?
for 10 minutes?
Okay, okay. So his total lecture is 10 minutes.
Okay.
So maybe we can wait for 2 minutes, Sensei, and otherwise, we can go ahead.
So if we can start now, maybe we can start now for this.
Yeah,
Or
actually,
maybe,
who are I know available candidate? We can start, Sensei, from.
but actually maybe it's better to wait 10 minutes because the people, yeah.
Okay, okay.
Okay. So we're going to start from 2:45.
Okay, Sensei. Okay, Sensei.
Yeah.
So we can
we're so
wait for
sorry
his
about,
time. Yeah, we can wait
yeah,
for his time, and after that. Okay.
yeah. We're so sorry about this inconvenience for the audience. We're going to wait for 10 minutes.